next 2 minutes. I'm hoping this works. Is my pen working? Yes, it's working. All right. All right, to all the future people in future years who are listening to this, I apologize for all the dumb stuff I'm about to do, okay? All right. So when we look at polarity over a much bigger, more complex molecule, it gets a little harder to tell what's going on. So up here, this is actually a fatty acid. Have you guys heard of fatty acids before, like omega-3 fatty acids and stuff like that? This is actually what they look like. Okay? When we look at a fatty acid, down here where we have a bunch of carbons and hydrogens, so all these carbon-hydrogen portions right here, are they polar or nonpolar? Pretty nonpolar, yeah. Again, we're being pulled equally on either side by those hydrogens. But when we're looking up here, at this area where we have some oxygens, this area right here is kind of polar. But the fact that we have a huge area of nonpolar and a tiny little area of polar means that as a whole, this molecule is probably going to be nonpolar. Okay? Right down here, this is a more complex version, actually, of this. This is fat. This is actually what butter looks like in its most elemental form. This is butter right here. So we got a bunch of carbon and hydrogen, the little H2s right here. Just denote hydrogen on either side. It's a shorthand way of denoting hydrogen on either side. Okay. So these chains down here of carbon and hydrogen, are they polar or nonpolar? Definitely nonpolar. And this small little head up here, polar. But as a whole, this molecule, definitely nonpolar. Now you're probably going, why in the world do we worry about this? Okay. Well, we're going to get to water later on. We're going to get to the properties of water, and we're going to talk about how water interacts with polar and nonpolar molecules. Okay, so here's where we're starting to dip our toes in just a little bit with polar molecules. So we're just focusing on polar molecules now, and we're taking actually water itself as an example. Where's my pen? Thank you. All right, so we have that oxygen, which is very electronegative. We have the hydrogen, which not very electronegative, kind of, sort of. The bond between them is polar covalent. This is a polar molecule, remember? Because this is a polar molecule, the electrons will spend more of their time hanging around the electronegative atom. Oop. Oh, my pen stopped working. I don't know why. Probably because I got it too far away. Okay, we'll figure that out later. So these electrons are going to spend more time hanging around oxygen, less time hanging around hydrogen. So what that means is you're going to have a partial negative charge, because what charge do electrons have? Negative. You're going to have a partial negative charge around the oxygen, and because the electrons have left the hydrogen, you're going to have a partial positive charge there. When we say partial, a full negative charge would be where an electron is transferred. Partial negative charge is just where the electron spends more of its time. It still kind of spends some time around the hydrogen, but not a whole lot. Okay. So in an ionic bond, in contrast, where the electrons totally are donated to one atom, that atom that gets the electron will get a full negative charge rather than a partial. So because of this area up near the oxygen of the water molecule is going to be sticky. It's going to be sticky. So think of magnets where one side is positive and one side is negative. You put a bunch of magnets in a box and you shake them, and the positive side sticks to the negative side. You take a couple water molecules and you shake them up. The positive side, the hydrogen, will stick to negative oxygens of other water molecules. All because, ultimately because of that polarity. So here we have in red, we have oxygen. In white, we have hydrogen. Is oxygen going to be partially negative or partially positive? Partially negative. Partially negative. Yeah, partially negative. And hydrogen partially negative or partially positive? Partially positive. Yeah, so what's going to happen when you stick a couple water molecules together, you're going to have the partial negative be attracted to the partial positive. And it's a very, very weak attraction, very transient, very, very short-lived. You can break it really, really easily. In fact, let's break some of those bonds right now. I'm turning on a water faucet. So what we did here, I was going to splash some of you guys in the front row, but then I thought better of it. So what we did there is we caused water molecules to flow past each other, and as they were flowing past each other, they were breaking and reforming these very temporary bonds. These bonds are called hydrogen bonds. And they're a type of force that exists between molecules rather than within molecules. So remember way back when, somewhere up here, oh, I got it on the first try. We said that there were two types of forces in atoms, the bonds within molecules and the bonds between molecules. So we just finished talking about the forces within a single molecule. Now we're moving on to the forces between molecules. So if you are a polar covalent molecule, you can hydrogen bond in biology. If you are a polar covalent molecule, you can hydrogen bond. Write that down. If you are a polar, my writing is not working so well here, polar covalent molecule, this is not working. My dramatic little writing on the screen thing is not working as well as I like. I can just circle things, it looks like. Yeah, I can circle just fine. Oh, maybe not. I'm going to leave this alone before I really mess things up. Okay. We're just going to leave it to circling and highlighting things instead of writing things. So if you're a polar covalent molecule, you can hydrogen bond. There we go. All right. So we're going to take a little bit of a roundabout here really quick, talk about the properties of water, and then we're going to come back to those polar, non-polar, carbon-based molecules and talk about how they interact with water. So one of the cool things about water is that it sticks to itself because of these hydrogen bonds. So because it sticks to itself, if you fill, say, a beaker full of water, you know when you overfill a glass or a beaker and it forms that little bubble on top where it's ready to spill over, but it doesn't quite? It's called a meniscus, I think. That's because, is it called a meniscus? Crap. Oh, it's like incurving, never mind. All right, I need to go back and review some of my basic chemistry. Anyways, so this bulging over without spilling over the side is called surface tension. It's called surface tension. That's because the water is hydrogen bonding to itself. It's sticking to itself. Okay. Now, nonpolar substances, on the other hand, they don't hydrogen bond. They don't really stick to themselves, at least not nearly as strongly as polar molecules do. Okay? So here's liquid water. We can see those little hydrogen bonds dotted here. Those water molecules are constantly moving past each other, breaking and reforming bonds. What's interesting about water, though, in particular, and this is kind of unique to water, when it freezes, look what happens. Those hydrogen bonds force the water molecules into these stiff, straight angles. So when you look at ice, it's actually more of a crystal than anything. So those hydrogen bonds, the angles of the hydrogen bonds force the water molecules apart, making ice less dense and way less than liquid water. That's why ice floats in water. All right. Now this here is not something you need to know, at least not yet, not until you're taking anatomy and physiology too. But this is kind of cool. All right, we went to all the trouble of learning this by now. Okay. So really, really quick background information before we learn this idea. Your lungs, so these guys right here, your lungs contain tiny little air sacs called alveoli, and they're itsy bitsy, they're microscopic. Okay. So alveoli look like this. Okay, they're tiny little sacs full of air When you breathe in air, it inflates these alveoli. And water coats the inside of these alveoli. All right, you are moist. So water coats the inside of these little air sacs. But what will happen to these air sacs is if water is allowed to coat the inside, and these alveoli are still very delicate, the water will stick to itself and cause the alveoli to collapse. Because water, well, it sticks to itself, and it will cause those sacs to just compress. So what our cells do in our lungs is they produce a molecule that breaks up the water, that prevents it from hydrogen bonding and prevents it from sticking to itself. It's called surfactant, actually. That's what that molecule is called. It's called a surfactant. And that allows these sacs to resist the tension caused by water and to fully inflate when you breathe in. So if you don't have this surfactant, your little air sacs can't fully inflate and you feel like you're drowning because you can't get enough air. Now, premature infants are actually have problems with this. One of the last things you do before you are born is you start producing surfactant. So premature infants, if they're born before they've started producing, they actually have trouble getting enough air. All because of water and hydrogen bonding and ultimately electronegativity. Did I just blow your mind a little bit? I know when I saw this I went, oh, I have to use this as an example. Alright, so we just looked at one type of chemical bond. We looked at hydrogen bonds. Hydrogen bonds are the most important type of intermolecular force. There's others out there, and there's a lot more than what are on this list. We're just going to look at a couple other ones that we're going to run across, especially when we talk about proteins. Okay. So again, just to define hydrogen bonds, and we'll look at these next two. Hydrogen bonds are temporary, weak bonds between the hydrogen of one molecule most of the time, and an electronegative, such as oxygen, atom of a totally separate molecule. Hydrogen bonds are weak. Hydrogen bonds are temporary, but together they are strong. So if you have thousands of hydrogen bonds, they'll hold you together.
So a hydrogen bond can exist even if hydrogen is not necessarily around them?
So a hydrogen bond can exist even if hydrogen is not necessarily around, yes. Yeah. Or something like a hydrogen bond. It's called something a little different. Yeah. So that's kind of the answer to your question, yeah. Now dipole-dipole forces, on the other hand, are temporary, very weak attractions between polar molecules. They're kind of like hydrogen bonds. They're what make polar molecules that don't have hydrogens sticky. And then one other type of force, van der Waals forces. All molecules have these. I love that word, van der Waals. Van der Waals. All right. Thank you to Simon Garrett for teaching me that pronunciation. My chemistry teacher. All right. So van der Waals forces are temporary, extremely weak attractions between any type of molecule, polar or not polar. Now, with van der Waals forces, though, and actually with all of these, if you add them all up together, if you get millions of different individual interactions, millions of different van der Waals forces, that can add up to something quite strong. So as an example, geckos. You know geckos, they like to climb up walls, right? So if you look at their little feetsies, their little feet actually have molecules that are very, very good at forming van der Waals connections, and very, very slightly sticky connections. So geckos, when they attach to walls, they'll use those van der Waals force to very, very lightly stick themselves to the walls and climb the walls. So that's how geckos work. All right. Let's actually take a 5-minute break, guys, and I'll hit pause on this. And then we'll come back after 5 minutes, and we shall resume our talk about water. So, continuing our talk about good old water, all right? What's that Adam Sandler movie, Waterboy? Water sucks. It really, really sucks. I've had that song, I swear, stuck in my head for 2 weeks at a time. Right? Gatorade. Do you guys know what I'm talking about? Please tell me you know what I'm talking about. Okay, good. Otherwise I sound like a total moron. More so than I already do. So water, contrary to Adam Sandler, is actually incredibly important. It does not suck. It is the most important biological molecule. And the reason why is because, well, A, it's freaking everywhere, and B, it is capable of hydrogen bonding. So, in order to understand why it's so important, we got to look at this rule in chemistry. Have you guys heard of this? Like dissolves like? Yeah, a little bit. Okay. So, what this means is that polar molecules will dissolve, or another word is solvate, okay, or they'll break apart other polar molecules. Non-polar molecules will solvate other non-polar molecules. But if you mix polar and non-polar, it doesn't work so well. They don't mix with each other. So if we take, say, oil, which is very, very non-polar, and water, and you try and mix them together, what happens? They separate. Yeah, exactly. So now here's the thing, though. Most biological molecules, the vast majority, well, not the vast majority, but most of them, are actually polar. So that means water can break them up. So why in the world are we not just little puddles of molecules then? Well, the parts of our bodies that aren't broken up by water are actually nonpolar. So your skin is actually quite nonpolar. You ever go out in the rain and water drops fall on you? It doesn't dissolve your skin, it beads up, right? So your skin is actually quite nonpolar. So many of your internal organs have nonpolar coverings, okay, that help actually to sort of protect you from this water you can kind of think of. Now what this also allows molecules to do when they are solvated is it allows them to slide past each other, to interact with each other, to exchange electrons with each other, and do chemical reactions with each other. You're a big walking bag of chemical reactions. Okay, and it's all because of water. Now water will also dissolve ionic compounds that are crystalline, so things like salt. You guys know that when you put salt in water, it'll just break up. And we need ions in order for our neurons to communicate, in order for our muscle cells to work, in order for our heart cells to work. We need them to be broken up. So without water, it doesn't work. You guys ever want a really neat demonstration of this, by the way? Stick out your tongue and then pat it really, really, really super dry with paper towels so there's no liquid on the surface, no water, right? And sprinkle some salt on your tongue. You won't be able to taste it. So not until you get some more saliva in there. You really got to get your tongue real dry because your cells, in order to register that they are receiving ions, or that they're receiving salt, they need that salt needs to be dissolved in liquid. Actually, I should have brought some paper towels and some salt. Okay. So here's where we're just highlighting what we just talked about. Here's oil right here. This is actually oil and butter are very, very similar in their structure. Remember, this whole area right here is nonpolar. All those carbon-hydrogen chains in this area right here is polar, but the nonpolar wins out. So we say this molecule as a whole is quite nonpolar. Here's polar water. When you try and mix the two, down here, this is what happens. Okay. Oop. Something that's kind of interesting, actually, soap. Does soap interact with grease? Yeah, it does. Does it interact with water? Yeah, it interacts with both. It's a magic molecule, right? So soap, when we look at the structure of a soap molecule, exactly half of the soap molecule is very, very polar, and half of it is very nonpolar. So the half that's polar interacts well with what? Water or grease? So the half that's polar interacts with water or grease? Which one? Water, yeah. The half that's nonpolar interacts with grease. So you can dissolve the grease using the soap and then wash it away using the water. Soap acts as a bridge. All right. So another property of water, as we just said, it can also dissolve ions. And if you take a crystal of ions right here, these are atoms that have donated their electrons from one atom to another, so they are in ionic bonds. Water, what it'll do, it'll surround that crystal, and look at that oxygen right there with the partial negative. That little circle right there means it's a lowercase Greek delta, means partial or small. So the partial negative on the oxygen will be attracted to the positive, on a positive ion. And meanwhile, the partial positive on a water's hydrogen will be attracted to the negative ion, and it'll strip away the ions from that crystal and allow those ions to float around inside a solution. And we had seen this earlier with this link at the bottom. This is the video with the squid, the dancing squid. We said as soon as you add salt to mussels, right, they start moving, they start communicating. That's because the salt is solvated, it's dissolved by the liquid in the soy sauce. Oh, I just gave away my soap example. Oh well. So, this is going to come back later as well though, because we're going to learn about some biological molecules that are this half magic nonsense right here. They are half polar and half non-polar. By the way, anybody happen to remember from high school biology what one particular molecule had this magical property in biology? Starts with a P. pH? PHO?
Phosphorus.
Almost.
I was thinking that too.
Phospholipid, actually.
Oh.
Have you guys heard of phospholipids? And some of us. Okay, if you haven't, not a big deal. You will by the end of tomorrow. So, molecules that are partially polar and partially non-polar, they can interact with both water and oil. And these special biological molecules that we're going to learn tomorrow, phospholipids are one of them. All right. So they will actually break up the surface tension of water. So if you took a little beaker of water and you filled it until it was overflowing and then you added a drop of soap, it'll spill over the sides. Not because you've overfilled it, but because you've broken the surface tension. And when you add these part polar, part non-polar molecules to a mixture of oil and water, guess what? They're going to mix together. This is actually the basis behind mayonnaise. So mayonnaise is a mixture of oil and water, right? And what do you usually add to mayonnaise besides oil and water and salt and spices and things like that?
Vinegar.
Vinegar? Okay, that's more water, yeah, essentially. Yeah. What else do you add? Eggs. Yeah, eggs have a lot of that special molecule that's half polar, half non-polar. Yeah, and the fat eggs, yeah, too. So, when you add an egg to that mixture, the molecules in that egg will cause the oil and water to merge. So, eggs and soap are good emulsifiers. They cause polar and non-polar molecules to mix together. Okay. So, soap is another one. As we said before, it solvates both grease and oil. The grease part using its non-polar tails down here, and the water part that it solvates. Dang it, pen, come on, start working. I swear it has a mind of its own, right? The water part will be up here on the polar head. Now a little interesting tidbit, you don't have to know this. Bacterial cell walls are made of a molecule very similar to oil, which means that soap disrupts their cell walls. And it kills them. Some bacteria, I should say. Okay, so some water terminology now. Now that we're sick of water, we're almost done with it. Okay. So we can use two special terms to describe molecules that interact with water or don't interact with water. Hydrophilic and hydrophobic. What does hydro mean? Water. Yeah, that one's easy. What about philic? Yeah, like or love. So a molecule that's hydrophilic loves to interact with water. What types of molecules love to interact with water? Polar molecules, yeah. So a lot of times we use the terms hydrophilic and polar interchangeably. And most biological molecules are hydrophilic. Same with ions. A hydrophobic substance, on the other hand, does not interact very well with water. What does phobia mean? Fear, like arachnophobia, fear of spiders. Exactly. And so a hydrophobic molecule is non-polar. It doesn't mix with water. It's not soluble in water, and this includes oil, fat, gasoline, too. Doesn't mix very well with water. Right? We saw that octane molecule earlier that didn't mix well, etc. Okay, now, acids and bases, the bane of our existence, pH and pKa and pOH and all that nonsense, right? We're not going to get too deep into this. It's a little bit scratching the surface, okay? So we're going to talk briefly about what acids and bases are, just so everybody's on the same page, and then why they're important in biology and what they do to us if we're not balanced in terms of our pH. So an acid is any molecule, it's any molecule that when you put it in water, an H plus will detach. It'll detach and float around in the water. So as an example, let's do this one. So I'm drawing the structure for vinegar up here. And when you put this molecule, no, I'm not missing one. When you put this molecule in water, this hydrogen right off the end right here, it'll actually detach from the rest of this. And so you'll increase the amount of hydrogen floating in water, and that's called an acid. Vinegar acts as an acid when dissolved in water. Now the opposite, where a molecule releases an OH instead, that's called a base. Both acids and bases in extreme concentrations, when you have a ton of H plus or a ton of OH floating around, can be pretty nasty for you. Our molecules don't like extreme amounts of H pluses or OHs floating around. Another definition, by the way, that you may have learned in chemistry, acids accept electron pairs, bases donate. We're not going to worry about that definition too much here. Okay, so the way we measure the amount of H plus or OH floating around in water is by using something called the pH scale. So pH scale starts at 1, goes to 14. An acidic solution, a mixture of water and an acid, has pH values of 1, 2, 3, 4, 5, 6, 7. Pure water by itself has what value? 7.0000, etc. Anything that's slightly basic will have 7.1, 2, 3, 4, 5, 6, 7, 7.1, 8, 9, 10, 11, 12, 13, 14, right? Give me a break. I started at 8:30 in the morning too today. Now, for most of our cells, most biological fluids range between 6 and 8. Where do we have a particularly acidic area in our body? Stomach. Yeah, we have a lot of stomach acid. Where do we have a particularly basic area of our body? What about our blood? Your blood is actually slightly basic. Same with the inside of your intestines too. If you talk about most of our body fluids, though, they're pretty close to 7. Actually, a little slightly basic, but for our purposes, pretty close to 7. Now, we can't tolerate really large changes in pH. So below 6 and above 8, we're dead pretty fast. Some bacteria can, though. Remember we talked about some of those extreme guys? What were they called, actually? Anybody remember what are those guys who love to live in really acidic, really inhospitable environments called? Yeah, some of the archaea, so they're not actually bacteria, but some archaea can really tolerate extreme pHs. In fact, they even like it. So here's our pH scale. On the bottom here at 14, really, really basic. This includes things like oven cleaner and bleach. Here we have a lot of OH floating around in our solution. At the top, at pH 1, that includes battery acid and a little less nasty stomach juice and lemon juice. Right? That's where we have a lot more H plus instead floating around in our solution. All right. So this is not something, again, that you need to know yet. This is for anatomy and physiology too. Okay, specifically I think like half a quarter. So one of the things that can happen to you if you don't breathe properly is something called respiratory acidosis. Respiratory acidosis. So again, a little bit of background here. Okay, carbon dioxide is what we breathe out. Right. So CO2 is what we breathe out. And CO2, through kind of a weird series of reactions, you're kind of just going to have to take my word for it right now. When it dissolves in liquid, it actually acts as an acid. So it acts indirectly as an acid, so it releases acid. Now, if you can't breathe properly and you can't exhale and get rid of that CO2, the CO2 builds up in your blood. Right? You actually carry carbon dioxide in your blood the same way you carry oxygen. Okay? And it'll actually make your blood more acidic over time. Now, when that CO2 increases and your blood becomes acidic, the pH goes down. Remember, low numbers on the pH scale are acidic. And that results in a condition called respiratory acidosis. And respiratory acidosis can be temporary, like when you hold your breath for a little too long. Right now I'm going to send myself into a very, very brief, very small version of respiratory acidosis. All right, and then I'm breathing in normally. Actually, that didn't work because I was exhaling CO2 at the time, so never mind. You can also get respiratory acidosis due to blocked lungs because of pneumonia, which is a lung disease, diabetes, obesity, where you're just having trouble mechanically ventilating, where you're having trouble just lifting your muscles up and down, or also smoking. Hopefully all these conditions are pretty temporary though. More long-term though, if you have weak chest muscles, so weak muscles up here and weak diaphragm down here, this usually happens as you age, your muscles weaken and atrophy. You can't properly push air out of your lungs, and so CO2 builds up, and your blood becomes more acidic. And if you have this, then you require treatment using something called a CPAP, continuous positive airway pressure device, in order to get that CO2 out. Have you guys ever heard of a CPAP device?
Is that one for like people snoring?
Is that the one for people snoring? A little bit sometimes. Yeah, sometimes it can be used if you're having trouble exhaling. Okay, and there's several sleep devices. This is just one of them. Okay. Oh, kind of cool, huh? All right, guys. Let's take another 5-minute break. Okay, then we'll come back. We have a little bit left. We're going to talk about carbon. Okay. So 5 minutes, get up, walk around. Alright, so let's talk about carbon. Let's talk about carbon. We've talked about water. We've talked about why water is important. Now we're going to talk about carbon and why carbon's important. So carbon has 4 valence electrons, which means it can form how many bonds? 4, it's right behind me. Yeah, exactly. So it has 4 valence electrons, which means it can accept 4 more electrons. And because of that, carbon can have single bonds, it can have double bonds, it can have triple bonds. You won't really ever see it have quadruple bonds though, because at that point your electrons are pretty darn crowded. Now, because it can have 4 bonds, it can form these really big, complex branching structures. And as we know, structure dictates what? Function. Yep. Now, most of the time, carbon will bond with itself. It will bond with hydrogen, nitrogen, and oxygen. These are actually the most common elements in the human body, as it turns out, right? So when we look at how these molecules are written out, oop, too fast? Okay, no worries. Let me draw you a couple examples of these complex structures. So we can have something that looks like this, just a chain. We can have something that looks like, whoop, like that. That's more of a tetrahedral. We can have things that look like rings. Right? We can have things that are even more complex than this, that can pop out in 3 dimensions. All right. You okay?
Yeah.
Cool. Thank you.
Thank you.
No worries. So when we write out these big carbon-based molecules, a lot of the times we end up with hundreds of carbons, thousands of hydrogens, hundreds of other molecules. So we get kind of lazy. We get lazy when we write these out. So we actually have sort of a shorthand form that we use to write these out. And a lot of times they look really bizarre. So here's an example of one of these shorthand organic molecule forms. There we go. No, it's not working again. Dang it. Never mind. I'm just going to draw it on the board. Technology, right? So I'm drawing what looks like a seagull on the board. That's a carbon-based molecule right there. I'm going to draw a hexagon on the board. That's a carbon-based molecule. So one of the ways we write out these organic molecules is by using things that look like this. And on these structures, there's rules to interpreting these structures. And one of these rules is at every bend and end. Every bend and end in here, there will be an invisible carbon. Okay, and the bend and end thing is my invention. I like it. I'm going to patent it. No, I don't think you can actually patent that, but I'm going to try. Okay, so every bend and end, we actually have a carbon sitting there. Okay. Now here's the thing about carbon. How many bonds does it need to have to be happy? 4. Yep. So if you look at the carbons in a hexagon, this carbon at the very top, at the very apex of that hexagon, how many bonds does it already have? 2. 1 and 2 on either side of it. How many more does it need? 2 more. Now here's the thing. In these structures, everything but carbon and hydrogen are explicitly written out. So if you see nothing but lines, you can assume it's all carbon and hydrogen. So here, this carbon already has 2. We're going to add 2 more hydrogens. Okay? There's no more bends and ends for us to fill in carbon, therefore the rest of it has to be hydrogen. This carbon right here already has 2 bonds. How many more does it need? 2. And what am I going to fill those bonds with? Hydrogen. What about this carbon? How many hydrogens does he need? 2. What about this carbon? 2. I'm going to get even lazier now. I'm going to compress it into just CH2 instead of writing out the stick with the hydrogen on the end. What about this carbon? 2. So I'm going to add 2 hydrogens. H2C is the same as CH2. What about this carbon? 2 hydrogens. So that's the whole structure. And when we look at this is kind of messy to just look at. It's way easier to just draw the hexagon, isn't it? When we look at this one, is there a carbon here at the end? Yes. What about here? Yes. What about here? Yes, here. And there at the end. This hydrogen already has 1 bond. How many more does he need? 3. Therefore, how many hydrogens does he get? 3. H3C. This carbon gets how many hydrogens? 2. This carbon? 2. This carbon? 2. And this carbon on the other end? 3. So this molecule is this molecule is actually pentane. It's actually pentane. Now, on these things, only the carbon and hydrogen are hidden. Everything else, if there's an oxygen, if there's a nitrogen, if it's a phosphorus, it'll be there. Okay, it'll be there. So we actually just drew out this first example. This is actually butane rather than pentane. It has 4 carbons instead. And we'll look at this one, this ring with the double bond on the other hand. We already know there's going to be a carbon here at one end of the double bond and the other end of the double bond. Right? We know there's going to be carbon here, 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 and here. How many carbons does this, or how many carbons, how many hydrogens does this carbon at the top of the apex get? 2. Yeah. What about this one? 2. This one? 2. This one? 2. This one? Ooh, 1. The one at the end of the double bond gets 1. The double bond counts as 2. So this carbon already has 1, 2, 3 bonds. It only needs 1 more. What about this carbon? 1. It has a double bond. It only needs 1 more hydrogen, therefore. You okay with this? We're going to look at this one, on the other hand. This Y-shaped molecule with the OH on the end. Okay. Here's where we're getting into having oxygens and phosphorus and whatnot. There's a carbon here at the end. Here at the end, did I miss any? Yeah, there's one right in the middle. Is there one right here? No, there's already an oxygen there. Leave it alone. Okay? You got good tenants sitting in your house, you don't kick them out. Okay? So that oxygen stays. Now how many hydrogens does this carbon at the bottom get? 3. How many hydrogens does this carbon on the left get? 3. What about this carbon in the middle? 1. It already has 3 bonds. 1, 2, 3. 1 hydrogen. Do we do anything over here? Do we add hydrogens? No. They're already there. There's already a hydrogen there attached to the oxygen. The only things that are hidden in these structures is carbon and hydrogen attached to carbon. All right. A little more complicated. So this is where we start seeing things like biological molecules. This right here, this is actually part of a structure of an unsaturated fat. This right here, this is part of the structure of a nucleotide. So you can see, and I'm not going to bother drawing these out for you guys because we've mostly, I think, got a handle on this, I think. Okay. So we can see that it's a way easier to look at this than it is to look at this. It's way easier to look at this, kind of, than it is to look at this full nucleotide structure. Okay. So you're going to see these and these. Very rarely you're going to see these two, not only in this class, but in pretty much all future biology classes that you take. If you guys take organic chemistry or the biological chemistry class that we have, you're going to learn way more about these carbon skeleton structures. How many of you guys have actually learned this before? All right, so many of us. Cool. All right. Our last bit here. So last little tidbits. Carbon, because it can form so many different structures, it can rearrange itself very easily. So we call these rearrangements isomers. An isomer is a molecule that has the same number and types of atoms, but slightly different structures. And as we know, if you change the structure, what do you change? The function, exactly. So right here, we have butane, okay, 4 carbons. This molecule, very, very nonpolar. It's like gasoline, okay. Here's isobutane. Isobutane is an isomer of butane. Ignore the little N part on here. They behave very, very differently. They behave very, very differently, even though they have the same number and types of atoms. So they are both isomers of each other, but they behave very differently. This is actually a very, very important when it comes to drugs. So drugs are just collections of a couple dozen carbon atoms bonded together with oxygens and hydrogens and things like that. So let me show you an example. So here, this is ibuprofen. What does ibuprofen treat? Headaches and pain and things like that. So in this right here, this is a slightly different way of writing out molecules. In black, every little black bulge is a carbon. What's the white? Hydrogen. What's the red? Oxygen. Okay, so it's kind of weird to look at, but it was the best image I could find. So ibuprofen has one isomer, and then here's the other isomer of ibuprofen. One isomer has a certain shape. It is effective. It actually works to relieve headaches. The opposite isomer with the same number and types of atoms, but different arrangements, it doesn't work. It doesn't do anything for you. If we look at albuterol, what does albuterol treat? It's right there, asthma, right? Here's the effective version of albuterol. Here's the isomer of albuterol. Doesn't do anything. Drug companies, what they love to do, in their infinite wisdom, is they will produce a drug that has a single pill that has both the effective isomer and the ineffective isomer. They'll market it to you and they'll say, hey, this works great. And then when their patent runs out, when they can no longer make money on that drug, they will just sell the pill that has only the effective isomer. So they'll isolate that effective isomer and repackage it and resell it to you saying, now with more, with more effective ingredients, now 10 times more potent, right? In reality, both work almost exactly the same. So the only case where, the only situation where this may be a concern for you health-wise is if you happen to be allergic to the non-effective isomer. But most people, you don't have to really worry about it. Interesting, huh? Have you guys heard of like Prilosec and Nexium? What do they treat? Heartburn. They're heartburn drugs, yeah. So Prilosec is the version that has both isomers, effective and ineffective. Nexium, which is way more expensive, by the way, has only the effective version. They both have the exact same dose of the effective isomer. So the Nexium pill is a little smaller, right, but it has the exact same doses as Prilosec. Stinky, isn't it?
What's the point of adding the ineffective isomer?
What's the point of adding the ineffective isomer? So a lot of times, chemically speaking, it's easier to manufacture a pill that has both rather than trying to put all the extra time and effort into isolating just the effective one, yeah. And also maybe for, they're preserving their intellectual property down the line too, so they can isolate and repatent and remarket the new version as well. Okay. One special type of isomer is called a cis-trans isomer. A cis-trans isomer. This only occurs around double bonds, and the reason why is because double bonds are not flexible. Most of the time with these chemical bonds, they can rotate, they can move around, they can wiggle. With double bonds, they're stuck, they're rigid with space. You can't rotate around them. So a cis isomer is where there's a carbon-carbon double bond, and there's two of the same atoms on both sides. So 2 hydrogens on one side, 2 CH3s on the other. What does trans mean?
Opposites?
Yeah, or opposite or across, rather. So here the hydrogens are across from each other. The CH3s are across from each other. Just tuck this into the back of your mind right now, because when we get to fats, we're going to be talking about trans fats. Have you guys heard of trans fats?
Mm-hmm.
Guess what they're named after? Trans isomers. They're actually the trans isomer of cis fats. So we're going to learn why trans fats are bad for you.
So trans cross can also be synonymous with opposite or
Can trans also be opposite, synonymous with opposite? I actually don't know. In most, most contexts I usually just think of it as a cross. Does anybody know? Can trans also mean opposite? I'll look that up for you. Okay, I know. We're almost to the end, guys. We're almost there, okay? We're almost there. Our last bit here, functional groups. Functional groups. Phew! With these, you do not have to memorize these. Just be able to recognize them. Okay? Just be able to recognize them. So a functional group in a molecule are small little chunks that we see over and over and over again, and we name them. Okay? So as an example, go into the next slide. Right here on this molecule on glucose, we see OH, 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 OH over and over and over again. So we just call that little chunk, that little OH, a special name because as it turns out, OHs react in special ways. So we call OHs in particular, we call them hydroxyls. And here's the structure of OH. The R right here just means a big other part of the molecule. A thiol is an SH. Thiol is SH. How many guys in here have naturally curly hair? Anybody? Curly hair? Curly hair? Yeah. So I actually kind of have naturally curly hair too. I just straighten it. But if you have curly hair, you actually have lots of thiol groups in your hair that bond with each other. And that's what causes your hair to curl, the bonding. If you have straight hair, you don't have a whole lot of thiol groups in there. And what straightening your hair does is it breaks the bonds between the thiol groups. Right here, this CH3, that's a methyl. Okay? So right here, this CH3 on the board, that's a methyl. That's a methyl. I feel like Oprah. You get a methyl, and you get a methyl, and you get a methyl. amino. So an amino group can either be NH2, it can have 2 hydrogens. It can also have 3 hydrogens. In some special cases, it can even have 1 hydrogen. That's why there's a little 3 halves there. Phosphate looks like this, PO4. Okay. How many of you guys grow plants at home? You guys know that you need to fertilize your plants regularly using phosphate, right? Well, if you didn't, you know now. So phosphate is actually necessary for cells to build DNA. We find a lot of phosphate groups in DNA. An acetyl group, on the other hand, I don't have that up here. I actually couldn't find a good example of this one. Acetyl, this one we're not going to encounter immediately. It's one that we're going to see when we talk about how cells use molecules, when we talk about metabolism. This is what acetyl looks like, a C double bond O bonded to an OH.
What happened to the methyl part of
Yep. Shit. Sorry. Thank you. I was writing carboxyl up on the board, not acetyl. This is acetyl. So C double bond O CH3. Thank you. I need a break too, but. So again, with these, you don't need to memorize them. You don't need to be able to write them out. Just if we point at a molecule and we say, oh, the hydroxyl bonds with the acetyl group over here, you need to be able to kind of recognize them. All right, these are just little shortcuts, ways of remembering things. All right. So here's what I want to do next. I'm actually going to hit pause on this because we are done with chemistry. So bye-bye. I don't know why I'm waving because you can't see me, but bye.